Hello, everyone. Today, we begin a fascinating chapter called
Orienting Yourself, the Use of Coordinates.
Space by itself is chaotic. To describe any exact location, mathematics needed a system powerful enough to convert physical position into numbers. That system is called the coordinate system.
But this idea did not suddenly appear in modern Europe. Thousands of years ago, the cities of the Sindhu-Sarasvati civilization were already built on precise north-south and east-west grid patterns. Streets intersected systematically, allowing locations to be identified accurately using distance and direction. This was an early practical form of coordinate geometry. Later, Indian astronomers developed this idea further. Ancient scholars used Ujjayini as a central reference meridian for measuring locations across regions. Aryabhatta introduced advanced trigonometric methods to map celestial objects, while Brahmagupta formalized zero and negative numbers, concepts absolutely essential for the modern coordinate plane. Without negative numbers, most of the Cartesian plane would not exist. Today, the same mathematical framework powers satellite navigation, robotics, architecture, computer graphics, and modern physics. And this entire system begins with two simple perpendicular lines. To locate any point in a plane, we draw two axes. The horizontal line is called the x-axis. The vertical line is called the y-axis. Their intersection point is called the origin. The origin has coordinates 0, 0. It acts as the universal reference point for the entire plane. Positive x values extend toward the right. Negative x values extend toward the left. Similarly, positive y values move upward, while negative y values move downward. The two axes divide the plane into four regions, called quadrants. Quadrant 1 contains points where both coordinates are positive. Quadrant 2 contains negative x values and positive y values. Quadrant 3 contains both coordinates negative. Quadrant 4 contains positive x values and negative y values. Now, consider a point represented as xy. This ordered pair gives the exact position of the point. The first value, called the x-coordinate or abscissa, represents the perpendicular distance from the y-axis. The second value, called the y-coordinate or ordinate, represents the perpendicular distance from the x-axis. And the order is extremely important. 3, 5, and 5, 3 are completely different points. A small change in order creates an entirely different location in the plane. Coordinates allow us not only to locate points, but also to measure distance geometrically. Suppose two points are connected diagonally. How do we calculate the shortest distance between them? This is where the Bodhayan-Pythagoras theorem becomes important. The horizontal displacement between 2 points is x2 minus x1. The vertical displacement is y2 minus y1. Together, these form a right triangle. Using the Pythagorean relationship, we obtain the distance formula. This formula is one of the foundational tools of analytical geometry. It allows distance to be calculated algebraically without physically measuring anything. Modern GPS systems, computer graphics engines, and digital mapping technologies all rely on this same mathematical principle. Coordinate geometry also introduces the idea of symmetry and transformation. When a figure is reflected across the y-axis, every x-coordinate changes sign, while the y-coordinate remains unchanged. Similarly, reflection across the x-axis changes the sign of the y-coordinate. But something remarkable happens. The shape changes orientation, yet all distances remain exactly the same. This property is called geometric invariance. Reflection changes position, but preserves magnitude and shape. That is why reflections are called isometric transformations. By the end of this chapter, coordinates stop feeling like simple points on graph paper. They become a mathematical language capable of describing motion, symmetry, structure, and space itself. Coordinate geometry is where algebra begins to visualize geometry, and geometry begins to think numerically. Because mathematics is not merely about numbers, it is about creating systems powerful enough to describe reality with precision.